Okay, let's talk about some material from lecture 20. This is more stuff on confidence intervals. Of course, watching videos is no substitute for reading the book and notes. I remember what we did last time. We talked about finding Z confidence intervals. A Z confidence interval with, say, level of confidence C, and C was usually something like 90% or 95%. And we assumed that we knew the population standard deviation sigma. And that kind of worked like this, right? If you think of the x-bar axis, let's just put mu here. If you start thinking about where sample means are, right? We're thinking of using a large enough sample, or perhaps we have a well enough behaved population, right, that we can assume that the CLT guarantees us that X bar will be pretty close to normally distributed. So right, this looks like this. And then what we wanted to do, well, what a level of confidence of, let's say, 90% means is that we're looking for an interval here called mu minus E to mu plus E. We're looking for an interval so that 90% of all the sample means would be in that interval. More generally, so that C would be a fraction C of the sample means would be in that interval, which is the same thing as saying that this area underneath the x-bar curve and between mu minus E and mu plus E is this number C. And even though we know this population standard deviation, we couldn't find these numbers mu plus E and mu minus E in the usual way because we don't know the population mean. So what we did is we transformed these things over to the z-axis. The mean comes over as 0, of course, in that transformation. Mu minus E is going to come over as some number, we called it minus z sub c. And mu plus E comes over as some number z sub c. And the area in between those two and under the standard normal curve is C. But under the standard normal curve, you know the mean and standard deviation. So you can actually find these numbers, these cutoffs for the area C in the middle. And then you can transform back. Z sub c comes back as mu plus E, and minus z sub c comes back as mu minus E, and now you have your cutoffs here. Well, when you don't know the population standard deviation, right, all you can do is approximate it. And what you do is approximate it by the sample standard deviation. What else have you got? It turns out that if you do that, you end up with a kind of similar picture, but not really exactly the same. So let's suppose this is the x-bar curve here. And so the mean mu is here. I'm going to put the z curve here. Okay. What we do when we approximate the population standard deviation by the sample standard deviation is we use that, and I'm not going to specify any details here because this is just to give you an idea of where the thing comes from. We use that to find an approximation to the x-bar, the PDF for the distribution of the x-bars. It's not going to be quite normal, this approximation. It's not going to be quite normal, but it's going to be close. It's going to be lower in the middle, and it's going to be thicker out at the tails, right? More area in the tails and less in the middle than the x-bar curve. What that means is that if we want confidence level C over here, right, if this is mu minus E and this is mu plus E, if we want the same area in the middle, but we have a lower, flatter curve in the middle and thicker tails, we got to go out a little farther. Right? This is going to be mu minus, let's say, E1. I'm just going to call it that. And then over here, we're going to have mu plus E1. And the area between those is our number C, our confidence level C. Well, now, transform. And what do you get? You get a curve that looks very much like the standard normal curve, but it is lower in the middle and thicker in the tails. And this curve is called T. It's the PDF for a thing called the student T distribution. Right? For historical reasons, it's called the student T distribution. It's in the book. You can look it up in about 10 million places on Google. Well, these numbers come across as, well, we would call them minus T sub C and T sub C with the area C in between. The mean of all the T curves is 0. There are a lot of them, and I'll talk about that again in a second. The mean of all the T curves is 0, right? And it turns out we can find these numbers. Right? There's a way to find these numbers, these T critical numbers as they're called. And then we do the same deal. We transform them back to here, and that gives us these two numbers here, mu minus E1 and mu plus E1, which gives us a confidence interval. Now it's a T confidence interval. It's a T confidence interval for the population mean. It's going to be a little wider than the Z confidence interval, but we can't get the Z confidence interval because we don't know the population standard deviation. So we settle for this T confidence interval. All right, let me say a few more words about this T distribution thing. Just a couple. In general, if this is the standard normal curve, so this is the Z curve, those T curves are all lower in the middle and higher out at the ends than the Z curve. The mean is always 0, as I said before. Right? But this might be the curve, the T curve for n equal 5, right? That means sample size 5. The T curve you end up using depends on your sample size. If you had a larger sample, it would be a little bit lower in the tails and a little bit higher in the middle. So let's say you might have this curve right here. This might be the curve for n equal 12, say. Well, it turns out that by the time you get up to n equal 30, you're pretty close to the plain old standard normal curve. Right? So as n gets closer and closer to 30 here, going up, right, the T distribution gets to be a better and better approximation for the Z distribution. And so T confidence intervals get to be better and better approximations of Z confidence intervals. All right, I've just gone through a bunch of stuff, and we're not actually going to use any of it directly. Right? We're going to do this stuff with the calculator, but I got to tell you something first. Right? It is very important that you know when to use Z and when to use T. When to use Z and when to use T. Problems are not going to tell you. Right? Most problems anyway are not going to tell you. They're going to give you a problem and you'll have to decide. And so you need to get this difference into your bones here, along with always check whether you can use the CLT. Right? In fact, step 1 here is, if you can't use the CLT, you don't use either one. You can't construct any kind of confidence interval if you can't use the CLT, if you can't apply the central limit theorem to guarantee the approximate normality of the sample means. Right? What you should do in real world, so in problems you would just answer, I can't do this. I can't construct a confidence interval here because the CLT can't be applied. In real work, what you should do is stop and call a professional. You should say to yourself, okay, I can't use the CLT. I am out of my depth. I need help. Okay. If you can use the CLT, it's very simple. If you know sigma, the population mean, you use Z. If you don't, you use t. Now in problems, the only way you can know the population standard deviation is if the problem tells it to you. Almost all these problems, except the ones that just give you data, almost all these problems are going to give you some standard deviation. What you'll need to do then is determine whether the standard deviation given to you in the problem is from the population or is from a sample. If it's from the population, then you have sigma and you should use z. If it's from a sample, then you don't know the population standard deviation unless it's given to you separately, but that doesn't really happen. If you don't know the population standard deviation sigma, then you should use t. Okay, let's do a couple of examples. So, in a random sample of 15 DVD players brought in for repair, the average repair cost was $80 and the standard deviation was $14. Assuming that repair costs are approximately normally distributed, use your calculator to construct a 90% confidence interval for mu. Okay, so first question, can we use the CLT? Right. The sample size here is 15, right? 15 DVD players brought in for repair. Right? So the sample size is 15, and that's too small. However, we are told that repair costs, that's the whole population, repair costs are approximately normally distributed. So yes, we can use the CLT. That's checked off. Now, the question is Z or T? Do we use a Z interval or a T interval? The problem gives us a standard deviation. But listen, it says, in a random sample of blah, 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 the average was 80 and the standard deviation was 14. That standard deviation is for those 15 DVD players. That is, it's a sample standard deviation. Right? It's a sample standard deviation. So we don't know the population standard deviation, and we have to use T. All right, we're going to do this on the calculator. So let's do it. Right, so first of all, you're looking for a function called T interval. It looks like this in the calculator, T interval. And it's on the stat menu, so you hit stat, and then you arrow over to where it says tests. Then you have to go all the way down to number 8 there, T interval. Press enter to put that on the screen. Now the first choice you have to make is between data and stats. Right? Data is for when you have just a plain list of data. Stats is for when you're given things like the sample mean and the sample standard deviation and the sample size. So you're going to choose stats. Whichever one you choose, you're going to put the highlighting on it and hit enter. By the way, if I go over to data and hit enter, you can see I won't have any place to put in things like the sample mean and the sample standard deviation. So I got to get this on the right thing. Put the highlighting on stats and press enter. Then you just arrow down and start putting stuff in. X bar, that's the sample mean. Here, the average repair cost was 80, so that's the sample mean. Then the sample standard deviation, we're told that that was 14. And now the sample size, which is 15. And the confidence level, 0.9. And then you just go down and go down to calculate and hit enter. And in a second, there's your T interval, right? 73.633, comma, 86.367. Okay, let's do this one. Construct 90 and 95% confidence intervals for the mean of the population from which the following sample data was taken. So this time, you're going to be constructing confidence intervals from data. Well, first of all, can you use the CLT? When can you use the CLT? When you have a sample size of at least 30 or the population is approximately normally distributed. Now, you can count if you like, but I'll tell you there are 30 points here, so we can use the CLT. And now the next question is it Z or T? Well, you can only use Z if you know the population standard deviation. And nothing in this problem says anything about the population standard deviation. So we're going to use t. This is going to be a t interval with data. All right. So what would I do? I'd hit stat and then edit, and I'd put all the data in the list L1. And actually, I've already done that. You put the data in list L1. Once it's in there, you just go to t interval, stat, go over to tests, down to number 8, t interval. Then you arrow over to data and hit enter. Okay, you have to put in what list it is. That should say L1, and you should just always use L1 for this. If it doesn't say L1, you can find the list identifiers above the numbers 1 through 6, right, and change it. But you shouldn't need to. Freak should stay 1. We never use that in this course. Confidence level, well, we have to do 90 and 95%, so we'll just leave that at 0.9. And now down to calculate. All right, there we go. 87.97 to 96.91. That's the 90% confidence interval for the mean of the population from which this data came. Now, if I want the 95% confidence interval, all I have to do is go over. The data is still in list L1, so I don't have to change anything except this. This is 0.95. Now I'll go down to calculate and hit enter, and there is the 95% confidence interval. All right, we got one more thing in this section, and that thing is minimum sample size. You know, if you're in charge of finding something out by polling or sampling, you know that every single measurement costs time and money. Right? So you want to use the smallest sample size you can while still getting the results you need. Right? So the results you need are often dictated by something like this. Estimate the mean of some population within 5 centimeters, or within some number of whatever they are. Right? Well, there you're actually given a margin of error, 5 centimeters or whatever, and you need to compute the sample size. So when we do confidence intervals, we're given a sample size and a level of confidence, and we have to compute a margin of error. Right? Here, we'd be given a level of confidence, C, let's say, and a margin of error, E. Given those things, find the minimum sample size. Find the minimum sample size that will let us estimate the mean, in our case, to within a margin of error E with level of confidence C. All right, here's how we go about it. I'm going to do a little algebra here, not much, but all you're going to need is the formula at the end. So remember, we have this. E is Z sub C times sigma over the square root of n. In this minimum sample size problem, we're going to know E, right? We're going to know C, so we can find Z sub C, and we're going to assume here that we know sigma. Right? Well, that means we can just solve this thing for n to get ourselves some kind of a formula. So let's multiply through by the square root of n. E times the square root of n is Z sub C times sigma. Now what I'm trying to solve for is n, so let me isolate it. Square root of n is Z sub C sigma over E. And that says that n, I'm just going to square both sides now, n is approximately equal to Z sub C times sigma, that quantity, over E, all squared. Now this may not turn out to be an integer, and so what you would do is you would round the approximation up to the nearest integer. All right, so let's do an example here. The lengths of movies in Jesse's collection have standard deviation 14.7 minutes. How large a sample is needed to be 95% confident that the population mean will be within 5 minutes of the sample mean? All right. Let's go over here and remember the formula we're looking at. Oh, that's not it. N is approximately equal to Z sub C times sigma over E, all that stuff squared. In order to figure out N, then, we have to be able to read this stuff, these other things, out of the problem. In particular, you have to be able to read the margin of error out of the problem. The reason I'm emphasizing this is that it's usually, when students have difficulty with this kind of problem, it's because they're trying to compute the margin of error. And of course, you can't compute the margin of error because N is not known. So you have to be able to read all three of these things out. So first of all, what's C, what's sigma, what's E? C is easy. C is 0.95 because this is a 95% confidence interval. And we already know that that means ZC is about 1.96. Right? You can find it easily enough, but we've done it plenty of times. The standard deviation, the population standard deviation, we were given it. It's 14.7. What's E? E is how close you have to come, how close this approximation has to be to this population mean. Let me read the second half of this. How large a sample is needed to be 95% confident that the population mean will be within 5 minutes of the sample mean? Right? Now everything is in minutes here, so that means that E is 5. Our margin of error is 5. And now we just put the thing in the formula. N is approximately equal to 1.96 times 14.7 divided by 5, and all that squared. Right? That turns out to be about 33.2, which says that the minimum sample size is 34, not 33. I know that number is closer to 33, but you're not rounding, you're rounding up. Right? If you rounded down to 33, again, if you rounded this down to 33, you would end up with a sample too small to give you what you want. You need to round it up to 34. Okay, I think I'm done with lecture